Welcome class. In today's video we're going to build on what we talked about today in terms of forces, FBDs, and we're going to introduce one of Newton's laws, Newton's first law, and we're going to talk about inertia. So before we do that, we might want to ask the questions: what happens when? What happens when you're driving along and you suddenly slam on the brakes? Well, your car stops and your body does what? Your body continues to move. It continues to move as it did before. So it continues to move as it did before. You may also ask the questions: you make a sharp turn right, the car goes right, but your body does what? It's tempting to say it moves left, but actually it just follows along in the same path that it was going before. And these events can all be explained by Newton's first law. So they can all be explained by Newton's first law. What is Newton's first law? Well, it is part of Newton's collection of 3 laws published in 1867, which describe the relationship between forces and objects. It talks about how forces and objects talk, how they interact. It's sometimes known as the law of inertia. Put simply, it says that objects will continue doing what they were doing unless acted upon by an unbalanced force. Because of this, I like to call it the law of laziness, as I said in class earlier today. There's a description at the bottom, which is a little bit more defined in terms of using scientific language. If the net force acting on an object is 0, the object will maintain its state of rest or constant velocity. So it will keep doing what it was doing unless acted upon by a force. So how do we get to here? Well, on the shoulders of giants. Galileo's thought experiment, which happened sometime before Newton. So Newton's work built on the work of Galileo, and the thought experiment went like this: the ball speeds up as it goes down a ramp, as per the diagram, and it slows down as it goes up a ramp. So ball is going this motion, and it slows down going down the ramp. Speeds up going down the ramp, slows down as it moves up the ramp. So imagine if there was no friction at all between a ball and a ramp. So this scenario, the second scenario B, the ball would start at a certain height, which we might call delta dy, and it would find its way back to that height if there were no friction. The key here being, imagine there's no friction. That's a little bit less, not very real word, but imagine if the ball stops where it reached the initial height. So that was a thought experiment. Now, Galileo had the presence of mind to say, what if the ramp continued in a straight line? What if it actually continued in a straight line? Well, without friction or any other force to stop it, the ball would continue moving at a constant velocity forever. And that's very important, that the force is actually required to slow down the ball. So Newton put that into words and put it into a law and said that, we need a force to get a ball moving, and we also need a force to stop it. Otherwise, it will just continue at a constant velocity. So part of this involves inertia. Inertia is a concept which causes the ball to resist its change to its motion. When we say inertia, it's anything. It's a condition of matter. A description, characteristic of matter that resists its change of motion. So inertia is a property of matter. Anything that has mass and inertia, that is matter. Matter is defined as anything which has mass and inertia. Inertia can be seen as a resistance to a change of motion. And obviously, as you can see from the bubble on the right, the bigger the mass, the greater the inertia. So a body at rest will want to stay at rest. A body at motion will want to stay at motion. If we look at this diagram, you can clearly see there's a puck and a hockey rink. Now, if we look at the puck, you can see that the puck will, at the moment, the puck is at rest. The puck will continue to be at rest unless it's acted upon by a force. So the puck will do nothing, will continue as it is, but when a force acts on it, it can move right or left. So a hockey stick or so on, and that would be an applied force. So when a force is applied, we looked at FBDs earlier today. When there's an applied force, it will move it in the rightward direction. Now that hockey puck will continue to move in a constant velocity. So in a hockey rink, there's very little friction between the hockey puck and the ice. If we assume that there's no friction, that puck, in fact, would just continue moving at a constant velocity until acted upon by a force. So maybe when it hits the boards right at the end, so it would continue moving in a constant velocity until it actually collided with the board, and only then would it stop. So it will continue to move in that constant velocity until a force is applied, in this case by the boards. So some applications in Newton's first law, seat belts, so they don't allow your body to move forward once the car stops. So once a car is decelerating to a stop, your body would want to keep moving forward. It's the seat belts which prevent that from happening. Airbags, concussions, also, so there's a lot of sporting, a lot of sports overtones here and sporting applications. So many applications of Newton's first law, too many to mention here. Okay, so that is a brief introduction to Newton's first law. I want you to think about the applications in Newton's first law. Also, we will practice doing some FBD diagrams, and remember that when Newton's first law, a body will continue doing what it was doing, be it stopped or in motion at a constant velocity, unless acted upon by an unbalanced or net force. When there is a net force, then there is acceleration, and that moves us on to Newton's second law, which we'll talk about in further classes.